KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
NEET, JEE, IIT coaching experts from Rajasthan and Andhra Pradesh along with our effective teachers.
Admission registration for classes LKG to +2.
KURINJI Educational Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.com.
In continuation to the last class, in this class we start with problem number 9. See here, see the first problem in this class, that is problem number 9. A series Lcr circuit with R is equal to 20 ohms, L is equal to 1.5 Henry, L is equal to 1.5 Henry and C is equal to 35 microfarad. L is equal to 1.5 Henry and C is equal to 35 microfarad. 35 microfarad is connected to the frequency of the supply. Is connected to a variable frequency 200 volts AC supply. When the frequency of the supply equals the natural frequency of the circuit, what is the average power transferred to the circuit in one complete cycle? Okay, right. So listen carefully. A series Lcr circuit with R is equal to 20 ohms, R is equal to 20 ohms, L is equal to 1.5 Henry and C is equal to 35 microfarad is connected to a variable frequency, 200 volts AC supply, 200 volts AC supply, full stop. When the frequency of the supply equals the natural frequency of the circuit, what is the average power transferred to the circuit in one complete cycle, right? So in this problem, regarding the series Lcr circuit, they have given R value, capital R value and L value and capital C. So these three already you know resistance, inductance and capacitance. Connected to a variable frequency 200 volts AC supply, right? But you just understand the situation, what is present, where the problem is present and what he is asking, right? And he is asking what is the average power transferred to the circuit in one complete cycle. But when this should be happen, when the frequency of the supply equals the natural frequency of the circuit. When the frequency of the supply equals natural frequency of the circuit. Okay, right. Come to the point, that is what answer. See here. When the frequency of the AC source equals the natural frequency of the circuit, the impedance is Z is equal to R is equal to 20 ohms. Okay, are you okay with this? When the frequency of the AC source equals the natural frequency of the circuit, the impedance is Z is equal to R is equal to 20 ohms. This is the condition. At this condition, this is valid. The average power dissipated per circle That's the formula, P is equal to V square by R. The same formula here regarding the situation P average. P average is equal to epsilon RMS square. Epsilon RMS square divided by Z. That is equal to epsilon RMS square divided by R. That is equal to 200 square, because this is what they have given in the question itself. 200 square divided by 20. So 200 square divided by 20 means, which is equal to 2000 watt. 2000 watt. That is the average power dissipated per cycle. Right. Next problem. A radio can tune. Next continuation problem. See here. So 9th problem completed now. Now 10th problem. A radio can tune over the frequency range of a portion of medium wave. MW means, in the bracket he mentioned, medium wave. A radio can tune over the frequency range of a portion of medium wave broadcast band. So in the bracket he mentioned the frequency. That is what? 800 kilohertz to the 1200 kilohertz. Kilo means 10 to the power of 3. Full stop. If its LC circuit has an effective inductance of, if its LC circuit has an effective inductance of 200 microhenry, if its LC circuit has an effective inductance of 200 microhenry, what must be the range? What must be the range of its variable condenser? What must be the range of its variable condenser? Okay, right. So what I am saying is here, if its LC circuit has an effective inductance of 200 microhenry, what must be the range of its variable condenser? Okay, right. See here, see the answer. For tuning the frequency of free LC oscillations, for tuning the frequency of free LC oscillations should be equal to the frequency of radio wave. This is what the condition he is saying. So you please observe the question. Based on that we have to go for answer. Right. In the question he is saying that a radio can tune over the frequency range of portion of medium wave with this frequency. If its LC circuit has an effective inductance of 200 microhenry, what must be the range of its variable condenser? What must be the range of its variable condenser? That's what we have to find. So we have to find the variable condenser. We have to find the range of variable condenser. Range of variable condenser. Okay, right. So see this. For tuning the frequency of free LC oscillation should be equal to the frequency of radio wave. For tuning the frequency of free LC oscillations should be equal to the frequency of radio wave. Frequency of radio wave. Okay, right. The value of this frequency, that is the formula, F is equal to 1 by 2 pi into square root of LC. 1 by 2 pi into square root of LC. Okay, right. So what I am saying is, see here, see this, F is equal to 1 by 2 pi into square root of LC, no? Or C is equal to 1 by 4 pi square L F square. 1 by 4 pi square L F square. Okay. See this. Here it is what? Two things are there, no? For different frequency. First, when the frequency is 800 kilohertz. 800 kilohertz. C is equal to 1 by 4 pi square into this is what 800 into 10 power 3, no? This is what frequency, not L. It is the frequency, right? Frequency square is there, no? That's why 800 kilohertz means 800 into 10 to the power of 3 whole square into, this is what L value. L value is 200 millihenry, 200 microhenry, no? Then what is 200 into 10 power minus 6? 200 into 10 power minus 6, right? So this complete mathematical calculation, this is what 1 by 4 pi square into this value 800 into 10 to the power of 3 whole square into 200 into 10 to the power of minus 6. So this complete expression will give us 197.8 into 10 to the power of minus 12. Okay. So anyhow here this is what the rounding of this value will give us 198, and this is what the picofarad. So 10 to the power of minus 12 means picofarad. Similarly, when we are going to consider the frequency of 1200 kilohertz, the same formula, that is C is equal 1 by 4 pi square into L f square. Okay, so 1 by 4 pi square, and this is what f square, and this is what L. Inductance is same, no? That is 200 microhenry according to the given question. So that will give us 87.9 into 10 to the power of minus 12. 87.9 into 10 to the power of minus 12. Okay, that is what will give us 88 picofarad, because 87.9 means you can write it as 88, no? 10 to the power of minus 12 means pico. So 88 picofarad. 88 picofarad. Okay, right. Thus, the variable capacitor should have a range of about. Thus, the variable capacitor should have a range of about 88 picofarad to 198 picofarad, because it is 198, no? It is 88. So the variable capacitor should have a range of about 88 picofarad to the 198 picofarad. 198 picofarad. Okay, right. This is what variable capacitance of a variable capacitor, or as simple as such, range of variable condenser, range of variable condenser or variable capacitor. Right. Next problem, that is what problem number 11. See here. So they have given one picture in this problem. That's what I hope you are able to see this, right? So that is what picture is important to solve this problem. So the figure shows a series LCR circuit connected to a variable frequency, 230 volts source. Figure shows a series. See this picture, see this figure. So when I am saying the information, you have to observe the figure. So this is what inductor, and this is what capacitor, and it is what resistor, and it is the source of AC, a symbol of AC. Right. Figure shows a series LCR circuit connected to a variable frequency, 230 volt source. Here L is equal to 5 Henry and C is equal to 80 microfarad and R is equal to 40 ohms. Right. L is equal to 5 Henry, C is equal to 80 microfarad, R is equal to 40 ohms. Okay, right. Now there are three things. We have to answer in this problem. First, A is determine the source frequency which drives the circuit in resonance. Right. Next, B is obtain the impedance of the circuit. And the amplitude of current at the resonating frequency. Okay, right, full stop. Now C is determine the RMS potential drops. Across the three elements of the circuit. Right. So here we have to find out RMS potential drop. Okay. Show that the potential drop across the LC combination is 0 at the resonating frequency. Right. So in the C itself, after calculating the RMS potential drop, he is asking to show potential drop across the LC combination is 0 at the resonating frequency. Okay, right. So observe this picture, how the resistor, capacitor and inductor, connected in series, and what are the values of, right? So See the circuit, and now I have written there itself Vrms is equal to 230 volts. That is what they have given. And L is equal to 5 Henry given, and C is equal to 80 microfarad. But microfarad is not the SI unit, no. So when we are converting into farad, in place of micro, we have to write 10 to the power of minus 6. 10 to the power of minus 6, right. And R value as usual given, that is what 40 ohms. 40 ohms, right. Now there are three things to work out, no, to answer, right. First, A, we are saying the A. Determine the source frequency which drives the circuit in resonance, right. So the formula for resonant angular frequency is omega R is equal to 1 by square root of LC, no. So 1 by square root of L is 5, no, right, directly can substitute, and C is 80 into 10 to the power of minus 6. That is what finally 50 radians per second. So the resonant angular frequency is 50 radians per second. 50 radians per second. Right. Next, B. That is what B here. So B at omega is equal to omega R, because he mentioned here, no. See this. Obtain the impedance of the circuit and the amplitude of current at the resonating frequency. So at the resonating frequency, omega is equal to omega R. So you can also write omega into L is equal to 1 by omega C. Therefore, impedance, this is what Z is the impedance, impedance Z is equal to square root of R square plus omega L minus 1 by omega C whole square. Omega L minus 1 by omega C whole square is equal to R, that is equal to 40 ohms. That is equal to 40 ohms, right. Next, current amplitude, right. So generally, according to Ohm's law, I is equal to V by R, no. So here current amplitude is equal to V naught by Z. That is equal to V naught by R. That is equal to root 2 into Vrms. Root 2 into Vrms divided by 40, because R value is 40. Right. So now he is going to substitute the values. Root 2 means obviously 1.414 into Vrms is 230 they have given, divided by 40 will give us 8.1 amperes, right. That is what at resonance. So in the question itself he mentioned, and here also we mentioned that at resonance, right. Next, C. In case of C, determine the RMS potential drop. Determine the RMS potential drops across the three elements of the circuit. Right, full stop. So that the potential drop across the LC combination is 0 at the resonating frequency. Okay, right. So in C, determine the RMS potential drops across the three elements of the circuit. Right. So how to determine the RMS potential drop? First, IRMS is equal to Vrms by R, and Vrms is equal to 230, R is 40. That is what is equal to 23 by 4 amps. 23 by 4 amps, right. Now, potential difference across L. That is what Vrms regarding the L. That's why here they put L. The formula is generally I into R, no. So IRMS into omega R into L. IRMS into omega R into L. That is what just now we calculated IRMS. That is 23 by 4 into omega R is the 50. Omega R is the 50, and that is what L value is 5. 50 into 5. So finally, this value, that is potential difference across L, that is Vrms L, will give us 1437.5 volts. Sorry. Okay, 100. Okay, right, no problem, because it is a potential difference, no. So you can put volts, no doubt. 1437.5 volts. Right. Similarly, we have to find potential difference across C also. So potential difference across C, Vrms C is equal to IRMS into 1 by omega R into C. 1 by omega R into C. That is equal to 23 by 4 into 1 by 50 into 80 into 10 to the power of minus 6. 50 into 80 into 10 to the power of minus 6, that is equal to same value we are getting here. Same value means we need not look at here, just we have to solve this one. That is what, 23 by 4 into 1 by 50 into 80 into 10 to the power of minus 6. 80 into 10 to the power of minus 6. So will give us 1437.5 volts. So what can we say at last? Potential difference across R, that is Vrms R is equal to Irms into R, that is equal to, see here, potential difference across the LC combination at the resonant frequency, at the resonant frequency. See this one, not this one, this one. Potential difference across the LC combination at the resonant frequency is equal to Irms into omega RL minus 1 by omega RC. Okay. So this one and this one having same value, no? So it is what, 1437.5 volt, and this is also same 1437.5 volt. So if you subtract this one minus this one will give us 0. So potential difference across the LC combination at the resonant frequency is 0. Next, potential difference across R, that is equal to Vrms, here R, that is equal to Irms into R, that is equal to 23 by 4 into 40. 23 by 4, that's what we calculated here, into R value is 40 mm. So they have given in the question itself. That is equal to 230 volt. 230 volt. That is equal to applied RMS voltage as expected, because what is the applied RMS voltage? 230 volt, no? So here what is the potential difference across R? We are getting 230 volts. So what is the potential difference across LC combination is 0, no? So whatever the applied voltage we are giving, that only we are getting as we expected. See why we are getting this is 230? This is because the total potential difference across the LC combination is 0. So here we experienced, no? Mathematically we experienced here, that is the potential drop across the LC combination is 0. Okay, right. Now, so in this class we discussed 3 problems. So in this class the first problem is 9. Here he is asking to calculate average power transferred to the circuit in one complete cycle. The formula is epsilon RMS square by Z. Epsilon RMS given as 200 and Z value or R value as 20 ohms. So 200 square by 20, that will give us 2000 watts. And this is the important point we have to keep in mind. When the frequency of the AC source equals the natural frequency of the circuit, the impedance is Z is equal to R. Z is equal to R. Okay, right. Next, in the next problem, 10th problem, here he is asking to find what is the range, what must be the range of its variable condenser, right? Its variable condenser. So what is the information they have given? A radio can tune over the frequency range of a portion of medium wave broadcast band with this frequency range 800 kilohertz to 1200 kilohertz, right? Full stop. If it's LC circuit, okay, see here. So regarding the 10th problem, here he is asking to find what must be the range of its variable condenser. Okay, so with the help of this formula and based on this formula, you can write C as a subject. Here we are getting this one. For tuning the frequency of LC oscillations, right? The frequency of the, for tuning, the frequency of the free LC oscillation should be equal to the frequency of radio wave, right? So here itself, this is the formula for capacitance, and regarding this frequency, this is the value we are getting, and regarding this frequency, we are getting this value, so that you can say finally that the variable capacitor should have a range of about 88 picofarad to 198 picofarad. Okay, right. Afterwards, in this problem, he is asking 3 things based on these values regarding the series LCR circuit. One is determine the source frequency which drives the circuit in resonance. So like this, by using this formula you can find, and which we got as 50 radians per second. And then obtain the impedance of the circuits and the amplitude of current at the resonating frequency, right? See here. So this is what impedance we got as 40 ohms, and current amplitude we got by using this relation, we got 8.1 amps. Next, he is asking determine the RMS potential drops across the three elements of the circuit. That is what we got, potential difference across L and across C and across LC. So this is what potential difference across LC of the combination at the resonating frequency becomes 0 because these two values are same now. Right. Next, potential difference across R, we got it as 230 volts. This is equal to applied RMS voltage as expected. Here the reason you can say that is this is because the potential drop across the LC combination is 0. Okay, right. So in our next class we will continue with 12th problem. Thank you.